Imagine looking up at the night sky and knowing that somewhere out there, hurtling through the darkness at over 290,000 kilometers per hour, is a visitor from another star system. Not just any visitor, but one that's breaking all the rules we thought we understood about comets and asteroids. This is the story of 3I/Atlas, the third confirmed interstellar object ever detected in our solar system, and perhaps the most mysterious one yet. What makes 3I/Atlas so special? Well, it's doing things that have left scientists scratching their heads in amazement. Its tail flipped direction in a way that defies easy explanation. It's accelerating faster than it should. It's glowing with unusual metals that shouldn't be there. And some researchers are asking questions that sound like they're straight out of science fiction. Could this be something more than just a comet? Welcome to the fascinating story of 3I/Atlas, where cutting-edge astronomy meets genuine cosmic mystery, and where every new observation seems to raise more questions than it answers. Section 1. The Discovery. Our story begins in April 2024, when astronomers using the ATLAS survey, that's the Asteroid Terrestrial Impact Last Alert System, spotted something unusual in their data. ATLAS is a network of telescopes specifically designed to scan the night sky for potentially hazardous asteroids that might be on a collision course with Earth. It's like a cosmic neighborhood watch, constantly vigilant for anything that might pose a threat to our planet. But what they found wasn't heading toward Earth. In fact, it was doing something far more interesting. The object, initially cataloged with a temporary designation, was moving through space in a way that immediately caught the attention of astronomers. Its trajectory was hyperbolic, which is the technical way of saying it wasn't orbiting our sun in a closed loop like planets and most comets do. Instead, it was passing through our solar system on a one-way journey, having come from somewhere else in the galaxy. This hyperbolic orbit was the first major clue that this wasn't just another run-of-the-mill space rock. When astronomers calculate an object's orbital eccentricity, essentially how stretched out or circular its orbit is, they use a scale where 0 means a perfect circle, 1 means a parabola, and anything greater than 1 means the object is on an escape trajectory. 3I/Atlas has an eccentricity of approximately 2.7, making it one of the most extreme hyperbolic orbits ever recorded. To put that in perspective, most comets in our solar system have eccentricities less than 1. Even the famous Halley's Comet, which travels far beyond Neptune before swinging back toward the Sun, has an eccentricity of only 0.967. The fact that 3I/Atlas had such a high eccentricity meant one thing: this object originated from outside our solar system. As more observatories around the world pointed their telescopes at this cosmic visitor, the evidence became undeniable. This was an interstellar object, only the third one humanity had ever confirmed. The International Astronomical Union officially designated it as 3I/2024, with the I standing for interstellar. The Atlas part of its name honors the survey that first spotted it. The discovery was thrilling for the astronomical community. After Oumuamua in 2017 and Borisov in 2019, scientists had been eager to find more interstellar visitors. Each one offers a unique window into other star systems, carrying information about the conditions around distant stars. But 3I/Atlas would prove to be far more stranger than anyone expected. Section 2. What makes an interstellar object? Before we dive deeper into the mysteries of 3I/Atlas, let's take a moment to understand what makes an object interstellar and why these visitors are so incredibly important to science. Our solar system is like a cosmic island in the vast ocean of the Milky Way galaxy. The sun's gravitational influence extends far beyond the planets we can see, all the way out to the Oort cloud, a theoretical shell of icy bodies that might extend nearly a light-year from the sun. Everything within this bubble is gravitationally bound to our star, orbiting it in various ways. But space between the stars isn't empty. Astronomers have long theorized that the galaxy is filled with rogue planets, asteroids, and comets that were ejected from their home star systems millions or even billions of years ago. These objects drift through interstellar space, traveling between the stars at speeds of tens of kilometers per second relative to the galactic standard of rest. Occasionally, purely by chance, one of these interstellar wanderers passes through another star system. Given the vast distances between stars, the nearest star to our Sun is over 4 light-years away, such encounters are rare from any single system's perspective. However, astronomers estimate that at any given time there might be thousands of interstellar objects passing through our solar system. The challenge is detecting them. And detection is incredibly difficult. They don't emit their own light, so we can only see them if they reflect sunlight. They're moving fast and they're small, which makes them appear as faint, fast-moving dots in telescope images. Before recent advances in survey technology, we simply didn't have the capability to spot them consistently. Oumuamua changed everything. When it was discovered in 2017, it was the first confirmed interstellar object, and it immediately captured public imagination. With its elongated shape and mysterious acceleration, Oumuamua showed us that interstellar objects weren't just theoretical. They were real, they were detectable, and they were weird. 2 years later came Borisov, a more conventional-looking comet that nonetheless provided valuable data about the composition of material from another star system. Borisov behaved pretty much like comets in our own solar system, with a clear coma and tail produced by ice vaporizing as it approached the Sun. Now we have 3I/Atlas, and it's proving to be perhaps the most enigmatic of all. Each of these interstellar visitors is like a message in a bottle from distant shores, carrying information about the conditions around other stars. They tell us about planet formation processes in other systems, about the composition of materials around different types of stars, and about the dynamics of how planetary systems evolve and eject material into interstellar space. But 3I/Atlas is telling us something unexpected. Its message is written in a language we're still struggling to understand, and that's what makes it so exciting. Section 3. The journey through our solar system. Let's trace 3I/Atlas's path through our cosmic neighborhood, because understanding where it went helps us understand why its behavior is so surprising. When 3I/Atlas was first detected in April 2024, it was already well into our solar system, roughly around the distance of Jupiter's orbit from the Sun. But by working backward through its trajectory, astronomers were able to calculate where it came from and where it was going. The object entered our solar system from the direction of the constellation Ursa Major. That's the Big Dipper to most of us. It had been traveling through interstellar space for who knows how long, perhaps millions of years, before gravity from our Sun began to slightly curve its path. Even though it was moving at tremendous speed relative to our solar system, the Sun's gravity was enough to bend its trajectory into a hyperbolic arc. As 3I/Atlas fell toward the Sun through 2024 and into 2025, it was accelerating under the pull of solar gravity, just as any object would. It passed through the orbits of the outer planets, Neptune, Uranus, Saturn, and Jupiter, picking up speed as it went. During this inbound journey, astronomers around the world trained their telescopes on it, gathering as much data as possible. The big moment came on October 29, 2025, when 3I/Atlas reached perihelion, its closest approach to the Sun. At this point, it came within approximately 0.65 astronomical units of our star. To put that in context, 1 astronomical unit is the average distance from Earth to the Sun. So 3I/Atlas passed inside Earth's orbit, but outside Venus's orbit. This perihelion passage was crucial for 2 reasons. First, it was the point where 3I/Atlas was brightest and easiest to observe, because it was closest to both the Sun, which illuminated it, and to Earth, and it was the point where the Sun's heat was most intense, which could reveal information about its composition based on what materials vaporized and how. Now, as we're speaking in November 2025, 3I/Atlas is racing away from the Sun, heading back out into the outer solar system and eventually into interstellar space once more. It's already past its perihelion, climbing back up the Sun's gravity well, but still bright enough for telescopes to observe. By early to mid-2026, 3I/Atlas will likely become too faint for most telescopes to track as it moves farther from the Sun. Eventually, it will exit our solar system entirely, heading in a direction roughly toward the constellation Camelopardalis. After visiting our cosmic neighborhood for just a couple of years, it will return to the darkness between the stars, carrying with it whatever secrets it hasn't yet revealed to us. This brief visit, just a cosmic blink of an eye, is our only chance to study this particular messenger from another star system. That's why every observation matters, and why the strange behaviors astronomers have documented are so important to understand.
Now we come to perhaps the most scientifically intriguing aspect of 3I Atlas, its unusual nickel emissions. When astronomers study comets, one of their most powerful tools is spectroscopy. This technique involves splitting the light from an object into its component wavelengths, essentially creating a rainbow, and looking for dark lines or bright lines at specific wavelengths. Each chemical element and molecule produces a unique pattern of lines, like a fingerprint. By reading these spectral fingerprints, astronomers can determine what a comet is made of without ever touching it. When researchers pointed their spectrographs at 3I Atlas, they found something unexpected: strong emission lines from nickel vapor. Now, finding metals in comets isn't completely unheard of. Comets do contain some metallic elements mixed in with their ice and rock. And as a comet gets close to the Sun and heats up, some of these metals can vaporize and show up in the spectrum. Iron is commonly detected, and nickel has been seen before in other comets. But the nickel emissions from 3I Atlas are unusual for several reasons. First, they're being detected at relatively large distances from the Sun, where you wouldn't necessarily expect strong nickel emissions. Nickel has a relatively high vaporization temperature, about 2,913 degrees Celsius, which means it doesn't easily turn into gas. For nickel to show up prominently in a comet spectrum, that comet either needs to be very close to the Sun, where temperatures are extreme, or something else needs to be going on. 3I Atlas was showing strong nickel lines even when it was well beyond Earth's distance from the Sun, at distances where most comets show relatively little metallic emission. This is puzzling. Second, the ratio of nickel to iron in 3I Atlas spectrum appears to be unusual. In most solar system comets, when you see metals in the spectrum, iron is typically more prominent than nickel. But in 3I Atlas, the nickel lines are particularly strong relative to iron. Why does this matter? Because the nickel-to-iron ratio can tell us something about where and how the object formed. In our solar system, the nickel-to-iron ratio in different objects varies based on the conditions under which they formed. Asteroids from different regions of the asteroid belt have different ratios, for example. The unusual ratio in 3I Atlas suggests it might have formed under different conditions than most solar system comets, which makes sense given that it came from another star system. Third, and this is where things get really interesting, the presence of nickel at all in such abundance is making some scientists scratch their heads. Some researchers have pointed out that certain types of industrial alloys contain nickel in significant amounts. Stainless steel, for example, typically contains nickel. This observation has led to speculation, mostly from more unconventional researchers, about whether the nickel could somehow be related to an artificial origin. Before we go too far down that path, let's be clear. The scientific mainstream is not suggesting that 3I Atlas is an artificial object. The consensus view is that this is a comet from another star system, and natural comets can and do contain nickel. But the unusual properties have certainly raised eyebrows and sparked discussion. Professor Avi Loeb from Harvard University has been one of the more prominent voices raising questions about 3I Atlas. Loeb, you might remember, was also the scientist who suggested that Oumuamua might be an alien solar sail. He's now pointing to 3I Atlas's nickel emissions and other unusual properties as potentially interesting from an astrobiology or SETI perspective. Loeb and his colleagues have noted that if you were designing a probe to travel between star systems, you might use nickel-bearing alloys for structural elements because of their strength and durability. The fact that 3I Atlas shows strong nickel signatures combined with its unusual acceleration and other oddities is enough to make them think it's worth investigating thoroughly. It's important to understand that Loeb's suggestions are speculative and represent a minority view in the astronomical community. Most scientists studying 3I Atlas believe that natural processes can explain all of its features, including the nickel emissions. So what are those natural explanations? Several have been proposed. One possibility is that 3I Atlas is particularly rich in nickel simply because of where and how it formed in its original star system. Different stars have different compositions, and the planets and comets that form around them reflect those compositions. If 3I Atlas formed around a star that was particularly enriched in nickel, the comet itself would contain more nickel than typical solar system comets. Another explanation focuses on the comet's surface properties. Perhaps 3I Atlas has a surface composition or structure that makes it particularly efficient at releasing nickel vapor. For example, if the nickel is present in certain mineral forms that break down easily, or if the comet's surface has recently been refreshed by fragmentation or crust breaking, this could enhance nickel emissions. There's also the possibility that we are observing some kind of selective effect. Maybe 3I Atlas contains similar amounts of nickel to other comets, but for some reason, perhaps related to its temperature, composition, or the way sunlight interacts with its surface, the nickel happens to be more visible in the spectrum while other elements are less prominent. Some researchers have proposed that the detection of nickel might be related to the comet's impact history. If 3I Atlas collided with a nickel-rich asteroid or planet at some point in its history, either in its home system or during its interstellar journey, it could have incorporated that nickel into its structure. Impacts can melt and mix materials, potentially concentrating certain elements in ways that wouldn't occur during normal formation processes. The nickel mystery is a perfect example of how single observations can spawn multiple hypotheses. We have a fact. 3I Atlas shows unusual nickel emissions. We have multiple possible explanations, ranging from the mundane to the exotic. And we have ongoing observations that might help us distinguish between these possibilities. What we really need is more data. Detailed spectroscopy over time could reveal how the nickel emissions change as the comet moves and rotates. Comparisons with other interstellar objects, if we can find them and study them, would help us understand whether strong nickel emissions are common in interstellar visitors or unique to 3I Atlas. And theoretical work on how different formation conditions might affect comet composition would provide better context for interpreting what we see.
While we've been focusing on the strange behavior of 3I Atlas itself, it's worth stepping back and asking a bigger question. How do objects like this become interstellar wanderers in the first place? The story of how comets and asteroids get ejected from their home star systems is a tale of gravitational violence, planetary dynamics, and cosmic billiards played over millions of years. When a star system forms, it starts as a disk of gas and dust orbiting a young star. Within this disk, particles collide and stick together, gradually building up larger and larger objects. These grow from dust grains to pebbles, to boulders, to planetesimals, objects kilometers across, and eventually, in some cases, to full-fledged planets. But not all the material gets incorporated into planets. Leftover planetesimals remain scattered throughout the system, orbiting at various distances from the star. In our solar system, these leftovers include the asteroids between Mars and Jupiter, the Kuiper Belt objects beyond Neptune, and the hypothetical Oort cloud objects at enormous distances. Now here's where things get dynamically interesting. Gravitational interactions between these small objects and the giant planets can change the small objects' orbits. A close pass by Jupiter, for example, can fling an asteroid or comet into a completely different orbit, sometimes pushing it inward toward the Sun, sometimes throwing it outward toward interstellar space. Computer simulations of planetary system evolution show that this ejection process is extremely common. In fact, it's an integral part of how planetary systems clean up their neighborhoods. As giant planets form and migrate inward or outward from their original orbits, they gravitationally scatter countless smaller objects. Many of these get ejected from the system entirely. The efficiency of this process is staggering. Some models suggest that for every kilogram of material that ends up in comets orbiting a star, hundreds or even thousands of kilograms of material get ejected into interstellar space. If that's true, then the galaxy is absolutely teeming with interstellar comets and asteroids. We're just seeing the tiniest fraction of them, the ones that happen to pass close enough to our Sun to be detectable. So 3I Atlas was probably once a regular comet orbiting its home star, perhaps in an outer region of that system, equivalent to our own Kuiper Belt or Oort cloud. It had an encounter with a giant planet in its system at some point, maybe billions of years ago, maybe more recently. The gravitational interaction gave 3I Atlas a boost of velocity, accelerating it beyond the escape velocity of its star. From that moment on, it was an interstellar object doomed to wander the galaxy indefinitely. We don't know where 3I Atlas came from, unfortunately. While we can calculate its trajectory through our solar system with high precision, tracing it back through interstellar space is much harder. Space isn't empty. There are gravitational perturbations from nearby stars. The galactic potential affects trajectories, and we don't know the object's exact velocity millions of years ago, so we can't definitively point to its home star. However, astronomers can make educated guesses based on the object's direction of approach and velocity. It came from the general direction of Ursa Major, and its velocity is consistent with it originating from a star within a few hundred light-years of our Sun. But there are thousands of stars in that region, so narrowing it down further would require additional information that we simply don't have. There's something poignant about this, isn't there? 3I Atlas has been traveling for who knows how long, carrying a message in its composition and structure about where it came from and what conditions were like around its parent star. But it's a message without a return address. We can read some of what it's telling us, but we'll probably never know which stellar family it originally belonged to. The ejection process that created 3I Atlas is also teaching us about how our own solar system evolved. Our own solar system almost certainly ejected vast numbers of comets and asteroids billions of years ago during a chaotic period called the Late Heavy Bombardment. If other systems are ejecting objects at similar rates, then the interstellar population should be enormous. Some researchers have estimated that there might be trillions or even quadrillions of interstellar objects in our galaxy. At any given moment, a handful are probably passing through our solar system. They're just incredibly difficult to detect because they're small, dark, and fast-moving. This realization has important implications. It means that the material from one star system can be transported to others. Interstellar objects like 3I Atlas are cosmic messengers carrying information between star systems. Some scientists have even speculated that life itself might spread between stars via interstellar objects, a hypothesis called panspermia. If microorganisms could survive the journey, a big if, then interstellar comets could theoretically seed life from one system to another. Whether or not that's true, interstellar objects definitely transport chemistry. The organic molecules, water, and other materials in comets like 3I Atlas are being redistributed around the galaxy. In a sense, the galaxy is constantly mixing itself, ensuring that materials and chemical complexity get spread around rather than being locked up in individual star systems. Transmission end. Time completed, Adkin, billions of years.
First, the nickel emissions have perfectly natural explanations. Comets contain metals, and nickel showing up in a comet's spectrum is not unprecedented. The unusual aspects of 3I-ITLASS's nickel signature could be due to its formation environment around a different star, or to surface properties we don't yet fully understand. There's no need to invoke artificial origins to explain it. Second, non-gravitational acceleration from outgassing is extremely common in comets. Yes, 3I-ITLASS's acceleration has some unusual features, but so do many natural comets. Every comet is unique, with its own composition, shape, and rotation. The fact that we don't have a perfect model for 3I-ITLASS's behavior doesn't mean it's artificial. It means comets are complex. Third, the jet flip phenomenon, while unusual, has been observed in other natural comets. Comets are dynamic objects that change as they're heated by the sun. Sudden exposures of fresh material, changes in rotation state, and other natural processes can cause dramatic shifts in activity. Again, no need for an artificial explanation. Fourth, regarding the pattern of unusual properties in interstellar objects, we've only detected 3 of them. That's an incredibly small sample size, far too small to draw statistical conclusions. It's entirely plausible that we've just happened to detect 3 unusual examples due to pure chance, or due to observational biases that make unusual objects easier to detect. Fifth, and perhaps most importantly, there's a philosophical principle in science called Occam's razor. When multiple explanations are available, the simplest one that fits the evidence is usually correct. Natural explanations for 3I-ITLASS's behavior exist and are consistent with known physics. Artificial explanations require us to assume the existence of extraterrestrial civilizations, that they build probes, that those probes travel to other star systems, and that we've happened to detect one. That's a lot of additional assumptions. Improved detection methods are crucial. We need better algorithms for identifying interstellar objects in survey data, faster follow-up procedures, and ultimately more powerful surveys like Rubin that can detect these objects earlier and in greater numbers. Detailed compositional studies are a priority. We need better spectroscopy of interstellar objects to understand their makeup. This requires large telescopes with sensitive spectrographs and coordination to ensure these precious resources are applied when needed. Theoretical work on how interstellar objects form, evolve, and respond to stellar heating needs to continue. Models need to be refined to explain the observations we're making. This includes work on how outgassing produces non-gravitational acceleration, how cometary surfaces evolve, and how the journey through interstellar space affects these objects. Comparative studies will become increasingly important as we detect more interstellar objects. Statistical analysis of populations is more powerful than studies of individual objects. We'll want to compare interstellar objects with each other and with native solar system objects to identify systematic differences. There's also the tantalizing possibility of sample return missions. While enormously challenging, the scientific payoff of bringing back material from an interstellar object would be immense. We could study it in laboratories with techniques far more sophisticated than remote sensing allows. This remains a long-term aspiration, but it's worth keeping in mind as we develop deep space mission capabilities. The broader implications extend beyond just the study of comets and asteroids. Interstellar objects connect to questions about planet formation and evolution. How do planetary systems form? How common are different architectures? What processes eject material into interstellar space? Stellar evolution and nucleosynthesis. What are the compositions of interstellar objects? Tell us about the stars they formed around. Can we use this to study chemical evolution in our galaxy? The possibility of life beyond Earth. Could interstellar objects transport biological material between star systems? Even if not, what do they tell us about the building blocks of life and their distribution in the galaxy? The nature of the interstellar medium. How do interstellar objects interact with the gas and dust between the stars during their long journeys? What can they teach us about that environment? 3I Atlas, despite being just one object among trillions in our galaxy, serves as a focal point for all these larger questions. It's a concrete example that makes abstract concepts tangible. It gives us something specific to puzzle over, to debate, and ultimately to learn from. Section 17. The Human Dimension. Beyond the science, there's a human story to the discovery and study of 3I Atlas. Let's consider the people behind the observations and what this tells us about how modern astronomy works. Somewhere on the Hawaiian island of Maui, in the pre-dawn hours of an April morning in 2024, a computer algorithm was processing images from the Atlas telescope. The software flagged an unusual moving object, just another entry in a database of thousands of detections per night. But this one would turn out to be special. An astronomer reviewing the night's catches noticed the object's unusual trajectory. Alert messages went out to the worldwide network of asteroid and comet observers. Other telescopes pointed at the same region of sky, confirming the detection and refining the orbit. Within days, it became clear. This was something extraordinary, an interstellar visitor. This initial discovery involves hundreds of people. There are the engineers who built and maintain the Atlas telescopes, the software developers who wrote the detection algorithms, the observational astronomers who schedule observations and process data, the orbit calculators who determine trajectories, the coordinators who manage the flow of information through the Minor Planet Center and other clearinghouses. Then there are the hundreds of astronomers worldwide who drop their other projects to observe 3I Atlas. Every observation represents a choice. Time on a telescope is precious, and choosing to observe one object means not observing something else. Researchers had to write quick proposals justifying why studying this comet was important enough to interrupt scheduled observations. Telescope allocation committees had to make snap decisions about granting this time. Many of these astronomers are working on 3i Atlas in addition to their regular jobs. They might be teaching classes, advising students, serving on committees, and writing grant proposals, all while trying to find time to analyze data on an interstellar object that won't wait for anyone. Graduate students are writing PhD theses based on 3i Atlas observations. For them, this object represents not just a scientific curiosity, but a career opportunity, a chance to work on something cutting-edge and high-profile. But it also brings pressure. If the object fades before they can get enough data, or if another research group publishes first, it could affect their academic futures. There are also the amateur astronomers making contributions. These dedicated observers, using their own telescopes and their own time and money, are adding valuable data to the mix. Some of them take their hobby as seriously as professionals take their careers, and their contributions are genuinely meaningful to the scientific effort. Behind all this are the funding agencies that make it possible. Telescope construction is expensive. Running an observatory costs money. Researcher salaries have to be paid. Most of this comes from government funding, taxpayer money allocated to scientific research because society values understanding our universe. When we marvel at discoveries like 3i Atlas, it's worth remembering that these discoveries rest on a foundation of public support for science. They represent a collective decision that exploring the cosmos is worthwhile, that knowledge for its own sake has value, and that pushing the boundaries of human understanding is a goal worth pursuing. There's also the global nature of modern astronomy. 3i Atlas is being studied by observatories in Chile, Hawaii, Arizona, Europe, Japan, and elsewhere. Data is shared instantly across borders through electronic networks. Researchers from different countries collaborate seamlessly, united by their common interest in understanding this cosmic mystery. This international cooperation is one of the great strengths of modern science. Political boundaries that divide nations in other contexts become irrelevant when facing a common scientific question. The study of 3i Atlas is a collaborative effort of humanity, not of any single nation. There's also a pipeline from discovery to public awareness. Science journalists write articles explaining the findings. Press officers at universities and observatories craft press releases. Science communicators create videos and social media content. All of this helps connect the research to the broader public, ensuring that the discoveries made with public funding reach the people who ultimately support the work. And then there's you, the person listening to or reading this script right now. You're part of the story too. By engaging with this content, by being curious about 3i Atlas and what it means, you're participating in the broader cultural process by which scientific discoveries become part of our collective knowledge. The fact that people care about interstellar objects, that there's public interest in these discoveries, helps justify the resources devoted to studying them. It creates a feedback loop. Discoveries generate interest, interest supports funding, funding enables more discoveries. This human dimension reminds us that science isn't just an abstract process of gathering data and testing hypotheses. It's a human endeavor, carried out by real people with hopes and careers and lives, supported by societies that value knowledge and ultimately meaningful because we, collectively, find these questions fascinating and worth pursuing.